Hello students, welcome to the channel Statistical Hub. This is our lecture number 11 in the course SH201A. Okay, so till now we covered something about probability, then we covered something about random variable. Now we are going for some standard distributions. So in this first lecture, we are going to cover something about Bernoulli and the binomial distribution. Okay, so let's move ahead. So this is something about the Bernoulli distribution, but before moving to the Bernoulli distribution, we will go for some basic introduction, like what is the meaning of all these things. So I hope you remember what is a random variable. So in the last lectures, we have just covered that random variable is some sort of function, and this is a function from the sample space to the real numbers. Correct? Now moving ahead in that part, then we define that the random variable, they can be of two different types. They can be discrete random variable, there can be continuous random variable. So for the course of discrete random variable, we had the basic introduction, like that depends like what is the classification of the random variable, that depends on like which particular range set they are belonging to. So for a particular random variable, if the range set is coming out to be countable, it can be finitely countable or it can be infinitely countable. So in this particular setup, the random variable that we are going to get, that is your discrete random variable. Okay. On the other hand, we have just covered like what is the meaning of continuous random variable. So in that part, I introduced you with the term that if the set or the range set in which the random variable is belonging, if that range set is uncountable, then that random variable is continuous random variable. Okay. Now, then we covered like why do we need the random variable? So the most basic and the most general setup is like to understand the nature of a population, we try to denote the observations from the population in the context of a random variable. Correct? So we covered something that for a particular random variable, the random variable will be taking some certain values. If I just say discrete case, then it will be some x1, x2, and so on. And there will be a respective probability that will be associated. Correct? This particular setup that is known as a probability distribution. Okay, this is the probability distribution like P of 1, P of 2, and so on. Now the point is, some of these particular kind of random variable, they are defined in different sense. They are given some particular distribution names. So on that particular context, we are having the first distribution, that is your Bernoulli distribution. Okay, so let's go for the definition. So Bernoulli distribution is a discrete probability distribution for a random variable which takes the value 1 with the probability P and 0 with the probability 1 minus P. So what we are getting that X is some sort of random variable, and in the range set of X, if I say the support of X, we are getting only two observations. There is 1, there is 0. Okay. And you count the 1 to be your success and 0 to be the failure. So the 1 that denotes is success and the 0 that is your failure. Easy concept. And then we are saying that X random variable can take a value 1 with the respective probability P, and it can take a value 0 with the respective probability 1 minus P. Okay. More in general, if I try to denote or if I try to define this particular thing, then the way that we define this is known as standard Bernoulli distribution. Okay, now someone will say, sir, what is the meaning of the Bernoulli distribution? So technically, any particular random variable that is taking only two possible values, some A, some B, with the respective probability P and 1 minus P, that is a Bernoulli distribution. Just assume that like I'm highly drunk. So in that particular context, like my walk, like if I'm standing at this particular point and assume that like I'm highly drunk. So in that particular setup, maybe on the very next moment, I will be taking some step on the right or maybe some step on the left. Okay, so in this particular example, you can simply think that X can take value maybe 1, maybe minus 1. 1 on the right side, minus 1 on the left side, with a probability, let's say P, with a probability 1 minus P. So this is also an example of Bernoulli distribution. But in our courses, we generally go for the Bernoulli distribution that is in the standard form, where we are having the success that is taking a value 1 and the failure that is taking a value 0. So that is the meaning of the Bernoulli distribution or the Bernoulli random variable. So what we came to know that X is in this format, and obviously the P, that is the probability of success. So the probability that belongs to 0, 1. Okay. So you have to remember few of the terms. So denote that X follow a Bernoulli distribution with parameter P, and we are having the parameter that will be belonging to 0 to 1. Okay. So this particular notation that denotes the family of distribution. So this is definitely a family. This is a family of Bernoulli distributions. Okay. And in this particular distribution, if we fix a particular value of P, fix a value of P to get one population. One population means to say one particular distribution out of that particular family. Okay. So that is the idea of a Bernoulli distribution. Okay. Let's move ahead. Now we are having certain properties that for a Bernoulli distribution, the mean value will be coming out to be P. The variance value that will be coming out to be P into 1 minus P. Okay. And this is the probability function that we are having. And you have to find these values. So the expectation of X, that will be simply X into probability function of X. And you have to add for all the values of X. For the variance of X, we already had the formula. That will be expected value of X square minus expected value of X raised to the power 2. So if you simply solve these things, you are going to get the value P, and this value will be coming out to be P into 1 minus P. And like 1 minus P, that is also denoted by Q. Okay, so that means to say we are getting a relation that P plus Q, that will be coming out to be 1, where we are counting the P to be the probability of success. So the Q, that will be the probability of failure. So that makes sense. Like if there is a 30% chance that you will pass the exam, then obviously there is 70% chance that you will fail the exam. Right? So that is the idea about like what is it? Bernoulli distribution, certain properties. Okay. Now let's go for the proof of the mean and the variance. So we have to go for the expected value of the X. That will be 1 into P plus 0 into Q. So we are getting P only. Okay. In the same note, you have to go for expected value of X square minus expected value of X raised to the power 2. So if you solve this part, then that will be 1 square into P plus 0 square into Q. This part is 0. We are left with only P. So P minus P square, I'm going to get P into 1 minus P. Okay. So you have to memorize what is the mean, what is the variance of the Bernoulli distribution. Okay. Now there comes the concept of the moment generating function. So we know the MGF that is given by MXT, that will be expected value of e raised to the power TX. Simply you have to solve this particular part. So if I just go for the calculation part, then MXT, that will be expected value of e raised to the power TX, and X can take value 1 and 0. So go for e raised to the power T into 1 into P plus e raised to the power T into 1 and 1 minus P, that is the Q. So in this particular part, this part will be coming out to be 1. So we are left with e raised to the power TP plus Q. Correct? So you can just write in this format also that it will be Q plus P e raised to the power T. Okay. So for every distribution, you have to remember few things. So always remember the first point, the support of the random variable. Second point, the probability function. Third point, the parameter space. Parametric space. So parametric space is nothing, that is the set of all the possible values of the parameter, like for the particular family of distributions. Okay, we are having the parameter space, this thing. Then the fourth point, always remember what is the expected value of the random variable. Fifth point, remember the variance of the random variable. And the sixth point, remember the MXT, the moment generating function. So for every distribution, you have to memorize these particular parts, like whether you are going for some particular entrance exam, or maybe you're learning this particular distribution or anything for any particular concept, or maybe for your college course, university course, anything. Okay, let's move ahead then. Okay, so that was something about the Bernoulli distribution. Now we are having the second distribution that we have to take into consideration. That is your binomial distribution. So we can just think about this, like what is the meaning of binomial distribution? So I can take maybe one example. So what are all the, okay, let me frame one example. Yeah, okay. So assume that I'm having a lot of pens with me. So okay. So let's say I'm having these three different pens. Okay. Now the point is, let's say I'm placing these pens in front of me. These are the three pens. Now the point is, I have to pick some random pen. Okay. And I count like picking the random pen to be like my success. So if I say I'm having 3 pens, and if I have to pick the pen, there are two possible outcomes. Either I can pick the pen or I may miss it out. Correct? Now the point is the binomial random variable is something similar to this one. It says that you are having n number of trials and you are counting total number of success in those n trials. Like in my case, I'm having these 3 pens and I'm going to pick maybe some random number of pens. So maybe I'm going to get 0 number of success. Like these pens are placed at this place and I'm like, okay, I'm not picking anyone. So in that particular part, my number of success that will be 0, correct? So in that particular part, the number of success is 0, stating that there is no success. Okay. On the other hand, you can have maybe the choice that I'm picking up 1 pen out of the 3. So again, I'm having like 1 success, 2 failure. Like 2 pens are unable to be like picked up. Okay. On the other hand, we can go for x equal to 2. I may be picking 2 pens. Okay. I may be picking 3 pens, but I can't pick more than 3 pens. That makes sense because I'm only having the possibility of 3 pens. Okay, moving ahead in this part. So what did I just explain? I just explained that you are having n number of trials and we are counting total number of success in n trials. And you can see each of the trial, like every experimental thing, there are only two possible outcomes. Either there can be a success or there can be a failure. So that means to say in the binomial distribution, we are counting number of success in n number of Bernoulli distributions or Bernoulli trials. Okay, that is the idea. So binomial distribution describes the number of success in a fixed number of independent Bernoulli trials. Here, that is very important point. We are having independent Bernoulli trials. That means to say the first trial that is not affecting the second trial. The second trial that is not affecting the third trial and so on. So we are having the case of independence. Okay, in this particular part, there is one more point with each with the same probability of success. Like if you go for the first trial, the second trial, the third trial, and so on. So in every trial, the probability of success then must remain the same. The probability can't change. That is the idea for the binomial distribution. Okay, so we are having n number of fixed Bernoulli trials. Then we are having the P that is constant for all the trials. Third point, the trials are independent. So in that particular part, I'm going to define X, that is the number of success out of n Bernoulli trials. That is the idea. So denote X that follow some binomial distribution with n comma P. So in this particular part, you can see we are having two parameters. So the two parameters that we are taking up that are the n and the P. N being the number of trials, N being the number of trials, and P being the probability of success in each trial. Okay, very easy concept. You are having number of trials and the probability of success. These are being the two parameters in this case. Okay, now let's try to see like where the particular parameter space will lie. So we know the P that is being the probability. So it will belong to 0 to 1. Okay. Then we have the n, that is the number of trials. So if I go for n equal to 1, that is also a bird. Technically, if you say binomial, 1 comma P, that makes sense that you are having only one Bernoulli trial. So technically, this is nothing. This is something similar to the Bernoulli with parameter space P. Okay. So we can see that n can take value from 1, 2, 3, and so on. It can go till infinity, like number of trials. Okay, but like we are not going for the large sample theory, so I will just go for like n, 1, 2, 3, and so on. So if I go for the parametric space, and if I say this is my n, and you say this is the probability of success. So the success probability that can be from 0 to 1, and we are having the number of trials that can be 1, that can be 2, that can be 3, that can be 4, and so on. So we are getting the parametric space that is coming out to be this particular thing. Like any point that is lying on these lines, that will make one particular binomial distribution. So again, in this particular part, if you say n belong to the natural numbers and the P belong to 0 to 1, that again denoting family of distributions. And once you fix the value of n and p, you are going to get one particular binomial distribution. And that n comma p, that will be anywhere on these particular lines, the vertical lines that I got in this particular graph. Okay, that makes sense. So you can go, this is 1, 2, 3, 4, and so on. And on the class of 1 only, if I fix only this one, then we are going to get different Bernoulli distributions. So that is the parameter space for the Bernoulli also. Okay, so that is the idea. Now let's move ahead. Then we are having the, okay, now in this particular part, the things are very simple. So you are having n different places, 1, 2, 3, and so on. You are having n places. That is the n trials. And I am saying that X is the number of success. So that means to say, we need to get X places to fill the success. So maybe this is my first success, the second success, maybe failure, and so on, maybe failure. So out of these n places, you are having X number of success. So you are left with n minus X number of failure. Correct? Very simple idea. So in this particular part, you are saying that I have to choose X places out of n places to fill my success. So we have to go for the combination formula that we may have covered like in lecture number 3, when I go for the basics about P and C. So we are having n places. We need to choose X places to fill the success. And these X places, they will be having the probability of success. So the probability of success, that will be raised to the power X, and the probability of failure, that will be raised to n minus K. So that is the probability formula. Okay. So we are having the binomial distribution, and this will be the probability formula. They are just using the X equal to K, fixing the value. Then we are having the mean value, that will be coming out to be n into P. And if you go for the variance, that will be n into P into P. Now, one more point that I can observe in this case, NP, that is the expectation of X. And if you go for n into P into 1 minus P, that is your variance of X. Now, simply think, is expectation of X greater than variance of X, or expectation of X less than variance of X? Let's quickly go over this one. Okay, so we can simply observe that this NP, that is coming out to be some number, let's say some number K. Okay, you are also having the K at this place, and 1 minus P, that is your probability of failure. So being a probability of failure, this probability will be somewhere in between 0 and 1. Okay, so what we are getting, like if I go for strictly between 0 and 1, then I'm going to get that this is coming out to be a fractional number. And if you multiply by K, then it will be coming out to be smaller than K. So we are getting that variance of X that will be smaller than expectation of X. So remember this property, that in a particular distribution, when you are finding that expectation is greater than the variance of X, then this particular feature is reflected back by the binomial distribution. Okay, let's move ahead then. Okay, then the derivation for these parts. So if I go for expectation of X, that will be expectation of X summation K running from 0 to n, K into P raised to the probability of X equal to K. That is the probability formula. Now, if you go for the basic forms of like expectation that we covered in the last chapter, and then if you go for the properties of the binomial distribution, you are going to get NP. And if you go for the variance, that will be coming out to be n into P into Q. So you have to just go for the proper derivation. So try the proper derivation for this one to understand like how these things are coming up. Okay, moving ahead. Okay, did I miss out something? Okay, now we are having the concept of MGF again in this particular part. So we are having nxt, that is coming out to be e expectation of e raised to the power tx. Simply expanding, then again, if you simplify this thing, that will be coming out to be q plus p e raised to the power t raised to the power n. Now moving back to the previous page, and if I go for this derivation, or maybe for this derivation, now these things are coming out to be like very, very simple. I can go for like making use of the properties that we already covered. So we know if you say that X that follows some Bernoulli distribution with the parameter P, then the expectation of X that will be coming out to be P only. And if you go for variance of X, that will be coming out to be P into Q. Correct? Now the point is, if you say Y, that is simply nothing, that is summation Xi, I running from 1 to n. You are having n trials, and we are counting total number of success. So if you go for expectation of Y, that will be coming out to be expectation of summation of Xi and that will be summation I running from 1 to n expectation of xi. Simply you are going to get summation p I running from 1 to n. You will get n into p. Correct? The idea is like very, very simple. Then if you have to go for the variance of y, so that can also be written variance of summation xi. So you'll be getting, again, these are coming out to be independent. So that will be n into p into q. Just applying the properties of like expectation and variance that we covered in the last module. Okay, moving ahead. Then if you have to go for mxt, so that will be myt in my case, and that will be nothing. M of summation xi t. So that will be expectation of e raised to the power t summation xi. Okay, simply expand. So expectation of e raised to the power t x1 plus so on xn. And then again, if you apply the independence property and they are following the same distribution, so the individual part, the x1, the x2, and the xn, they are following the Bernoulli distribution. So we can make help of that one and we'll be getting something q plus p e raised to the power t for individual one, and we are multiplying them. And that is something that is constant, so that will be raised to the power n. So that's how we can get the expected value, the variance, and the MGF for the binomial distribution. Okay. Moving ahead now, this is the same thing that I just explained. The binomial distribution is the sum of the n independent Bernoulli random variables. So if xi is a Bernoulli random variable with parameter p, then if we go for summation of xi, that will follow a binomial with parameter n comma p. Okay. Now we are having some particular examples that you can think about, like the Bernoulli. For the Bernoulli distribution, if I go for, if you toss up any coin, then there can be success, there can be failure. Correct? So we are having like a lot of examples that you can think, like any example. If you appear for some exam, then like in some exam, you are having two possible things. Either you pass or you fail the exam, correct? So again, a Bernoulli distribution. Another example, maybe there is some MCQ exam at your school or the college. You are given maybe 10 problems. Okay. Now in these 10 problems, if I say I didn't study at all, and there are like 4 options and one is only the single correct. So in that particular part, the number of success out of n trials that will follow binomial. So in this one, x is my score, number of questions I got correct. The number of questions that I'm going to get correct, that is like x that follows some binomial, 10 comma some p. And if I'm having the probability of success to be 1 by 4, so x follows some binomial, 10 comma 1 over 4. Okay. So that is the idea. Like you can think a lot of examples and why it is required. So you have to go for hypothesis testing or maybe the confidence interval when we are having a population, and you have to go for maybe the hypothesis testing for population proportion. Okay, this is the population proportion. In that part, if you have to go for confidence interval for p, then also you are going to make use of the Bernoulli and the binomial distribution. Okay. So that is the idea, like how you can think about the Bernoulli and the binomial distribution. Okay, now this is just the summary. So we already covered like what is the definition. So we just covered the x, that is some Bernoulli distribution. We covered some y, that is some binomial distribution. We covered the probability distribution function. So you need to remember what is the probability distribution for both of them. You have to remember what is the expected value. So you have to go for expected value of y also. You have to go for variance of x, variance of y. Then we have to go for the mxt, you have to go for the myt. So these are the things that you have to understand, and we know like what is the importance of these distributions. So if I go for like very generic example, let's say this population 1, 0, 1, 0, and so on. So to denote this population, I may say that x that follows some Bernoulli distribution with parameter p. I'm assuming that this is the same structure for the complete population 1, 0, 1, 0, 1, 0. Maybe in some particular state, we are having maybe equals X ratio. So I can say the male to be 1, female to be 0. So that can be the case. So that's how like we can make the practical use of these type of distributions that we just understood. So that was all about the lecture number 11. I hope you are able to understand what is the Bernoulli and the binomial distribution. Hope to see you in the next lecture. Bye. Take care.